Hello, I'm Param Hanji, a PhD student from the University of Cambridge, and welcome to my talk on the comparison of single-image high dynamic range reconstruction methods, where I will discuss the caveats of quality assessment. This is work done jointly with researchers at the University of Cambridge and Linköping University. Let me first give you some background on single-image high dynamic range, or SI-HDR reconstruction for short. The starting point is a single exposure image taken with an ordinary low dynamic range camera sensor. The objective is to infer HDR information, which is no easy task. SI-HDR is thus a multifaceted problem with several challenges, such as inverting the camera response function, expanding the bit depth, and reconstructing underexposed as well as overexposed pixels. Among these, reconstruction of overexposed or saturated pixels is both the most challenging and the most relevant problem. Over the past 5 years, several methods have attempted to solve the SI-HDR problem, and each successive method claims to improve the state of the art. However, there hasn't been a rigorous subjective experiment to compare the different methods. Most papers rely exclusively on automatic quality metrics, but we don't really know how reliable those quality metrics are. We benchmarked 6 recent deep learning methods by running a pairwise comparison experiment on a diverse, previously unseen dataset. 14 participants looked at pairs of images on a 1200 nits HDR display, and we asked them to pick the image of higher quality. This is simply the image that better resembles a natural scene and contains fewer distortions. If we pick the input single exposure image as the baseline and assign it a quality of 0 GOD, this plot tells us how much better or worse each method is compared to our chosen baseline. We were a little surprised to find that only 2 of the 6 methods, HDR-CNN and Mask HDR, were preferred to the unprocessed input. It turns out that most methods produced artifacts, particularly in saturated areas, that our participants found objectionable. You can view the reconstructions of different methods for yourself on our interactive HTML viewer at this link. The magenta bar on the right represents the reference HDR image and is thus unsurprisingly the most preferred. Conducting such an experiment is time and resource intensive, and most papers present quantitative results using image quality metrics instead. We looked at a wide range of commonly used metrics in order to rank the methods. We considered both full reference metrics that compare a test image to the reference HDR, as well as blind or no reference metrics that compute scores using test image alone. Only a few metrics support direct comparison of HDR images, and most need to be adapted to HDR content by applying a nonlinear transform. Our objective was to investigate which of these metrics agree with subjective data that we collected. When we directly computed image quality scores, we were surprised to find that all quality metrics failed to predict the perceived quality of SI-HDR reconstructions. Consider, for example, these scatter plots of PU21 PSNR and PU21 SSIM that show very weak correlations with subjective data. Each dot in these plots represents a reconstructed image, and the different colors correspond to the different benchmarked methods. The Spearman's rank order correlation scores are under 0.5, which is definitely not good enough. A major problem is that quantitative metrics are highly sensitive to small differences in tone and color. These differences are unavoidable because most SI-HDR methods fail to correctly reconstruct the camera response function. Metrics fail because such differences affect all pixels in the image, while saturated regions account for a tiny portion of the pixels. You can see the differences in tone and color between the reconstructed image, X, and the reference image, Y. To help ignore such differences and encourage the metrics to focus on artifacts in saturated regions, we find a global smooth color mapping function that corrects the inaccurate CRF. We assume that each corrected pixel is a linear combination of the polynomial powers of the corresponding input pixel. Then, least squares provides the required polynomial coefficients common to all pixels. CRF correction enables metrics to isolate differences in poorly reconstructed overexposed regions, such as the red lamp in this particular scene. Next, we observe that the standard procedure of averaging scores across all images greatly improves metric performance. To see this, let me first show you scatter plots for a single scene. Here you can see that subjective data does not really agree with the metric. Here's yet another scene from our experiment. Again, notice the poor correlations. The reason for the poor correlations is that each metric introduces per content bias. However, such biases cancel out when the quality values are averaged across content. Coupled with the CRF correction, the predictions of a select few metrics such as PU21 PSNR and HDR VDP3 now agree much better with subjective data that we collected. This is reflected in the higher correlation coefficients as well. If you come up with a new method for SI-HDR reconstruction, we recommend the following evaluation protocol. First, run a blind metric after some nonlinear perceptual encoding, then match the tone and color with polynomial CRF correction that I described earlier, and compute HDR metric scores. Finally, apply the perceptual encoding to both the CRF corrected and the reference images and compute SDR metric scores. As for specific metrics, we recommend computing PSNR and VSI, the visual saliency index, after applying the PU21 encoding for HDR adaptation. The popular HDR VDP3 is a suitable HDR quality metric, and PEAK, or perception-based image quality evaluator, is a suitable blind metric according to our experiments. We do not advise showing results using other popular metrics such as SSIM or the deep learning-based model LPIPS, since they poorly correlate with our subjective data even after CRF correction. However, you may still need to run a subjective evaluation if the difference in metric scores is not large enough. Finally, we observe that metric predictions are noisy, and gains reported in most papers are not statistically significant. By studying the various sources of noise involved, we determine the minimum difference in metric scores required to confidently distinguish one method from another. Let me show you how we did this for PU21 PSNR. We first bootstrapped metric prediction errors and fit a parametric distribution. Notice that this distribution of errors is approximately normal. From the cumulative distribution, it is possible to find the threshold at which we can claim at the 0.05 confidence level that a given SI-HDR method is better than another. For PU21 PSNR, this required difference is about 3.47 decibels. Otherwise, if the difference between methods happens to be smaller, you're probably better off running a subjective study, since quality metrics are most likely unreliable. To summarize, we conducted a rigorous subjective experiment to rank state-of-the-art single-image HDR methods. When we compared results of the experiment to predictions of popular quality metrics such as PSNR and SSIM, we found the correlations to be strikingly weak. We thus propose a new protocol for benchmarking SI-HDR methods that relies on first correcting the camera response function. Finally, we identified the minimum difference in metric scores to statistically distinguish one method from another. Thank you so much for listening, and if you'd like to find out more, please check out the paper and related material.